Determination of load when assessing the overall longitudinal strength of a ship. This is Article 7.8 of the book Mechanical Systems Calculations of the Marine Facilities. Determination of load when assessing the overall longitudinal strength of a ship usually corresponds with the use of the following criteria and conditions that are common when checking the overall longitudinal strength of a ship. And this we can just mention two the most useful criterions like A and B. A, assessment of a fatigue failure under repeated cyclic bending of a ship, experiencing an alternating wave bending moment simultaneously with a constant bending moment in calm water, avoiding fatigue failure of a material affects the value of the safety factor. That is the ratio of the yield stress of the structural material to the equivalent stress found for the ultimate static load according to one or another hypothesis of the material strength. This is the first useful criterion of the ship strength. Another one, B, the joint verification of the overall strength of the hull for bending and shearing under the action of the maximum possible sum of absolute values without taking into account the signs of the wave bending moment and the moment when the bottom hits the water surface with possible slamming, as well as bending moment in calm water. This is the second one, where the used criterion of the ship's strength, the ship's hull strength. And in some cases, when checking the overall strength, it may also be necessary to take into account the torque action on the hull, the oblique symmetric bending, which is typical for assessing the strength of connection structures of the multi-hull ships. Yeah, if, for example, the other peaks or the other hulls of the multi-hull ship can be on the crest of the waves. For example, the fore peak of one hull of the multi-hull ship and the stern peak of the another one hull is on the crest of the another wave. So the connecting beach between the hulls of the multi-hull ship experience the oblique symmetric bending. So this could be also the subject of the consideration of the general strength of the ship hull. Let's consider the KCI. The ship characteristics assigned: the length overall 122 meters, the waterline length 116 meters, the breadth 20 meters, the depth 11 meters. A cargo load line draft 5.2 displacement at summer load line 9,150 tons. The cargo capacity 8,000 cubic meters of the liquefied natural gas. This is a new design of the bunkering ship for supply of other ships by the fuel of the liquefied natural gas. Other elements of ship used in the exercise. We have to know the shapes of the theoretical hull shown the drawing on the figure 7.8.1. This is the figure showing the shape of the ship hull. This is transverse sections. This is a port side of the ship. This is port side as well. This is a port side watching towards the ship bow. This is a port side watching towards the ship aft. The ship is symmetric, of the symmetric shape related to the diametric plane. So we just only have to consider just only one half of the ship side of ship shape of the ship hull. We have as well the numbers. Here numbers is numbers of the water lines, theoretical water lines. It is the original 1-0 water line, the fourth, second, third, fourth. This is a cargo water line, which corresponds to the displacement at summer load line 9,150 tons. Here is water line, the cargo water line. This is theoretical water lines from the first to seven. And between 6 and 7 theoretical water lines, we have the cargo water line. So 8, 9 is water lines. Besides, we have here the indication of the numbers of the theoretic frames. The theoretic frames characterizing the shape of the transfer section of the ship. J. So the water lines number we indicate as I. And the transverse sections shapes we have by the J number. The first J number is the original, excuse me, not the first, but the 0, 1. Next, we have numbers of the water lines, the first, second, third, etc. This is watching towards the ship bow. And we have as well the water lines watching to the stern, 20, 19, 18, 17, etc. So this is water line, this is the shape of the ship. Okay, to process with the submerged volume of the ship hull to find the volumetric displacement of the ship, to find such as the coordinates of the abscissa of the center of the submerged volume, we have to first use to set the so-called table of the ordinates of the theoretic shape of the ship. So this is ordinates. So we have the axis, not indicated axis here, but let's just explain that we have the abscissa axis directed towards us, perpendicular to the plane of the draft. They have ordinate axis directed maybe to right side or maybe to left side. It's not so much important because the ship we considered symmetric relative to the diametric plane. The DP is diametric plane. And we have applicate axis Z. Z is not so much important in our calculation. So we have the table of the ordinates of the ship hull shape. This is a number of the water lines, the fourth, second, fourth, etc., up to 7. 7 a little bit. The next one after the cargo water line corresponded the cargo displacement at load line. This is a load line, yeah. Water line, cargo is load line, we can say. And the numbers of the transfer sections I, 0, first, second, etc., till 20. Usually we have 20. Sometimes people can have more than 20, but this for the theoretical calculations as we have here, with the check of the strength of the ship hull, by the considering the redistribution of the Archimedes law along the ship length, the distribution of the submerged volume, the corresponding distribution of the floating force, buoyancy force. We probably enough accurate can consider the 20 for the approximate calculations for the technical degree of the approximation. Okay. What is the cargo? The ship transported. The composition of liquefied natural gas usually transported by ship includes 90% of methane. It could be from 85 to 91%, which has mass density of 0.66 H ton per cubic meter, as well as 10% of mixture of the gases ethane, which the mass density 1.263 ton by cubic meter. This is almost like the air, the density. This is light than the air. Propane with the density of 1.H72 ton per cubic meter, as well butane and nitrogen. This is a mixture of the gases as the cargo. We can appreciate what is approximately the total density of liquefied natural gas can be approximately estimated as 0.9 is 90% we have the methanus, and 0.1 of the rest gases, and we have 0.75 H ton per cubic meter. And I'm sorry. The total mass of liquefied natural gas cargo in the ship with the volume. So the ship contains two cargo capacities, each of the volume of 4,000 cubic meters. So together they are 8,000 cubic meters. And so the maximal amount of the cargo on board can be by this density with a volume 8,000 cubic meters. We have 1,064 ton. And as we have two the equivalent capacities on board, so by 4,000 cubic meters, that is each one 3,032 ton in each 10 completely filled. Okay, so perhaps we will consider not the full loaded ship, but partially loaded. Partially, just only with the cargo in just one of the capacities. We have to consider the most dangerous circumstances of the ship loading. The most dangerous can be if the ship is with the cargo in the aft, located aft capacity, and if the middle capacity for cargo is empty. So in this definite one case could be the maximal bending moment of a ship on calm water and with the ballast, to exclude the slamming factor. So let's consider what will be the displacement of the ship if we subtract the cargo in magnitude maximal possible in one of the capacities located to the fore from the aft capacity. If we subtract from the cargo displacement the permissible magnitude of the amount of the cargo in the middle one capacity located to the front, so we have two capacities, one in the middle of the ship, a little bit shifted to the front from the middle, and the second one is located to the aft of the ship. If we have to fill the capacity in the aft of the ship and empty in the middle, located a little bit to the front from the middle, so we will have the ship of the cargo displacement 6,180 ton, which correspond to volumetric displacement. So we can find the volumetric displacement. This is a weight displacement or mass displacement. We can divide the mass of the ship with a partially empty ship with not the cargo in one of the capacities, divided by the density of the ocean water, 1.025 ton per cubic meter, the density of the water in the ocean. Usual density of the water could be a little bit more, a little bit less. In the fresh water, it will be just only 1. But in the oceans, we have 1.25 or 1.28. It's not so much important for the calculation. And so we will have the volumetric displacement equal to 5,969 cubic meter, the distance between each of two theoretical water lines of the 7 ones at a draft of 5.2. So we have assigned the load line draft 5.2, and we divided it by the in the theoretical plane. This for 7 water lines, and about water line appropriate to water line number 7, the cargo water line. So if we divide the drafted cargo water line 5.2 divided by 7, we can find approximately the distance between each of two theoretical water lines equal to t divided by 7, 0.743 meter between each of the theoretical water lines couple. Oh, sorry. We can just as well indicate the formula for numerical determination of the distribution of the volume by the draft of ship. So the immersed area of each theoretical cross section using the method of trapezoid rule is determined as. So this trapezoid rule, we have the factor 2 because we consider the symmetric ship, and in the table of the Excel, we have just only 1/2 of the ship widths, because these are not from the diametric plane, the plane of the symmetry of the ship hull. So if we do 2 for the multiply by delta 2 is the distance between two theoretical water lines, multiplied by the brackets. In the brackets, we have the total of from 0 to 6 is up to water line number 6. We have 6 water lines. What is the, for example, the submerged area of the transverse section of ship indefinite G's theoretic frame, and there is a total of the ordinates minus the adjustment. Adjustment is the total of to the zero and the last one ordinates divided by 2. This is adjustment to the total. This is trapezoid rule. And I'm sorry. Yeah. This extreme ordinates, extreme, yes, the 0 ordinate and the 6 ordinate and the total of 6 from 0 to 6. Okay. This is a picture how the ship looks like. What we talk about, this ship looks like. This is a general view and the general arrangement. It's first capacity of the liquefied natural gas, the second capacity of the liquefied natural gas. Here we have the power installation, and here we have the maybe this is pods as submerged electric motor gondole with the propeller. So this is with a power installation here. Perhaps this power installation as well used the bunker fuel, the liquefied natural gas. So each capacity is 4,000 cubic meter, equal a little bit more than 3,000 ton. And we consider the case if we have no the cargo in the middle one. This is the middle one. This is the middle theoretic section. Middle theoretic section. This middle. We say that this capacity is the middle, but it's a little bit moved to the bow of the ship from the middle, and another one is the aft capacity. If we have no cargo in the middle capacity, have only in the aft, we will have the maximal bending moment. We expect that due to the lack of the submerged volume, the peaks of the ship, by the shape of the hull, we have the less of the volume, the peaks. And if we have no cargo in the middle, that is the maximal expecting the uneven distribution of not only the submerged volume of the ship along the ship length, but as well no even distribution of cargo of the weights, not only cargo, but as well the weights of the ship and any variable part of the ship weight, like fuel, the ballast, etc. Besides, the draft of ship is only 5.2 meters. This is not so big draft, so but maybe this is a bunker ship. This works nearby the harbors, or maybe with the reasonable proximity from the harbors. So it has to be available to go to harbors and to moor to the berths of the no big depths, with a no big depth. So 5.2 meters low draft, and to exclude the slamming, if we will have only cargo in the aft capacity, the ship will have the not only the maximal bending moment, but as well the ship will perhaps will have the trim to the aft. So the danger is another one, that when the ship move with the trim to the aft, there perhaps could be the slamming of the bottom in the board part on the surface of water, if the ship has trim to the aft due to uneven distribution of the cargo, the absence of the cargo in the first capacity, but only availability of the cargo in the second one. So in this case, with the uneven distribution of cargo, we have to take the ballast in the bulk capacities, and we have about 1,000 ton in the bulk capacity of the water ballast, to keep to exclude the slamming by the water to the bottom of the ship, exclude the inappropriate trim to the aft, and to do the navigation more safe. So, but the use of the ballast in the bow part and in the aft part, this leads to increase of the bending moment in the middle part, because we have very small buoyancy in the bow part and the aft part, but maximal buoyancy we have due to the completeness of the hull in the middle part, although the cargo will be in the aft part and in the bow part. So we have to expect the maximal bending moment, what we need to do the check of the ship's strength. So we will consider the loading state of the ship with the cargo in the aft capacity of 3,000, a little bit more than 3,000 ton. And we consider the availability of the ship stocks, like the fuel, the variable stocks of the cargo, like a fuel of the ship, maybe the water, maybe fresh water for the ship consume, and the ballast besides of the stocks in the local to the bow part, to keep the trim in the appropriately within appropriate limits, and to exclude the slamming of ship when it moves in the water. Okay. So this is the result. Sorry, let's a little bit talk about how we have this result. This result for the transverse force and the bending moment diagram did on the stretched fiber. So this is a negative bending moment. So it corresponds to the shape with the bulge upward, with the bulge about the ship, due to the cargoes aft and the ballast and the stocks in the front part of the ship, in the fore part, and the exit of the buoyancy in the middle part. And this is the diagram of the chaining forces too. So let's consider how we have that. with the use of the Microsoft Excel program, the distribution of the immersed areas of the cross sections of the hull on the ship length, the submerged volume of by method of trapezoid, one determines this. We use the trapezoid second time, next is third time. The trapezoid method is very useful for the considered assure. So we have the dependencies used in the, we have the data, the ordinates, they use the ordinates to determine the ordinates got from the theoretic description of the ship hull shape. And we use this in the Microsoft Excel form, depends on the number of the waterline, that depends on the transverse section of the ship. We have this formula to find the area of the submerged part of the theoretic frame transverse section, and independence of the number, J is the number of the theoretic frame. This is a ship. This is the number of theoretic frames. The fourth, second, so etc. 20. 20 is the aft theoretic frame. The 0 is the bow theoretic frame. And the middle theoretic frame is 10. And this is theoretic frame the same from 0 to 20. 0 to 20 is a diagram, the bending moment diagram of the transverse forces. And we having the got dependencies of the submerged volume of, submerged area of the transverse section. We say Sj, we can find as well the submerged volume because we have the distance between each two transverse section of 20 theoretic sections of the hull, and having the area of each the transverse section submerged of the hull, and using the theoretical spacing between the sections, transverse section. Theoretical spacing is the length by the waterline. 116 we have by 20 spacings. We have 5.8 meter between each theoretic frame. So we have to use that, and we use this in the Excel as well. And besides, we need sometimes to have the coordinate abscissa. Abscissa means the axis along the ship with the length, corresponded with the length of the ship. We have to find the coordinate of the location of the submerged center of the volume of the ship hull. Okay, we need as well the static moment of the immersed volume of the hull. So we can find it as well using the got previously the areas of the submerged transverse sections by the theoretic frames. The areas, J is the number of the theoretic frame from 0 to 20 is. This is adjustment. This is adjustment to this by the method of the trapezoid adjustment. The extremal magnitudes of the 0 and the 20th transverse sections area, 0 and the 20th transverse section area. And this is L divided by 2 minus delta. Delta L is 1/20th part of the ship length of the ship by the waterline multiplied by J number of the theoretic frame. This show what is the abscissa relative the middle part of the ship, the middle theoretic frame. Middle theoretic frame is this is definite 1 point. And in the brackets for the finding of the static moment, we introduce there's a factor in the brackets. We have the abscissa L of the length of the ship divided by 2 minus delta L, delta L, the theoretical spacing multiplied by J number of the theoretic frame from 0 to 20. And this is the adjustments for the extreme magnitudes of the transverse section submerged of the theoretic frames. This is due to the rules of the trapezoid method, the adjustment we have to do. When stern cargo tank is lowered, the static moment at the immersed volume found by the Microsoft Excel program is equal to minus 11 H 5.1. So this is the magnitude of the static moment, and the abscissa of the center of the immersed volume located at the aft from the midship plane is equal to minus this static moment divided by the displacement of the ship, with not the cargo in the middle, in this one middle capacity, with absent of this cargo, the span, the cargo just communicated to the another one ship, and with just only cargo in the second one capacity, and with the definite required amount of the variable cargos like bunker and fuel, or maybe fresh water, or maybe the ballast in the bow capacity for the ballast and fuel. And 5969, this is submerged volume, volumetry displacement of the ship with not cargo in the first one, the first one capacity. Okay, so this is which one? The double. It is the cargo that W, excuse me, the W letter uppercase is the volumetric displacement of the ship with not the cargo in one capacity. And besides, we have to use the lightweight of the ship. What is lightweight? If the weight of the ship due to the load line is assigned 9,150 ton, this is total cargo in two capacities. Minus 1,000 is maximal magnitude, maximal amount of the of the variable cargos, like besides of the cargo itself, but the variable, I mean that the fuel, fresh water, or ballast we consider together. The magnitude have to be within the load line displacement. Maximal should be about 1,000 of ton. So we can find that the light weight of the ship is 2,086 ton. That is the weight we can transform using the gravity acceleration 9.81 meter per square second. We can find that it is 20,464 kilonewton, the ship weight, because we have to adopt the dimensions that if it is mass, we can say the ton, or maybe not in this definite one case, kilo, but ton or kilo, or if you are talking about the force of the weight, we have to consider as well the gravity acceleration 9.81 meter per square second, and this will be, considering the gravity acceleration, 20,464 kilonewton. The variable weight of the ship, its weight, which includes the weight of the cargo, one partially filled cargo of liquefied natural gas, and the weight of the supplies, which is 1,000 ton. This the cargo is partially weighted. This the full cargo possible here on board. Okay, distributions of the ship mass. The stern cylindrical tank that is located closer to stern of the ship with a cargo of the mass of 3,032 ton, weighing 29,744 kilonewton of liquefied natural gas, is distributed evenly along the length of the hull section in which the tank is located, in an area from 40.5 to 49.3 meter in stern from the midship frame. Yeah. This is a midship frame. This is aft capacity begin, 40.5 meter from the midship frame, the beginning of this capacity, and 49 here, the end of the capacity. The length of the membrane cargo tank is, this tank is 34.8 meter. For the one theoretical spacing, 5.8 meter, there is a load mass of 505.3 ton. That is, if we have the total mass of the cargo in one capacity, and the capacity length is 34.8 meter, and if the one spacing between the transverse sections, because we have to correspond the weights to the buoyancies, the spacing is 5.8, so we have to in the proportion 5.8 divided by 34.8 multiplied by the weight. We can find that for one spacing we have the load if the stern capacity loaded 505.3 ton. That is the weight of the 4,957.3 kilonewton. To use a ballast, it is required in the displacement of the supplies with a total mass of about 1,000 ton in bow ballast tanks located along the length of the ship in the range from 2.9 to 24.5 meter aft from zero theoretical frame, here from the bow perpendicular. In the plane of first theoretical frame, 5.8 aft from the bow perpendicular is the center of the mass of the hull. 500 ton of this ballast in the plane of the second theoretical frame, 11.6 meter from the bow perpendicular. This is the center of mass of the other half to the ballast. So we have the cargo in just only stern capacity distributed for 1, 2, 3, 4, 5, for 6, for 5 spacings. And we have distributed for 1, 2, for 3 spacing of the bow ballast in the bow. To balance the trim, to exclude the inappropriate trim, and to exclude the slamming the heats of the water when the ship is inappropriately trimmed to the aft with absence of the middle part of the cargo in the capacity number 1. Okay. So, yeah, in the plane of the first theoretical frame, 5.8 meter aft from the bow perpendicular is the center of the mass of the hull for 50 ton. Yes, we did talk about that. And what about the ship itself? The ship itself consists of the superstructures and the main hull. And the mass of superstructure we have to adopt could be about 20% of the ship light weight. That is of 2086 ton we got previously. The ship light weight we have 2096 ton. And the superstructure weight equals about 417.2 ton. That is the weight, considering the acceleration of gravity 9.81. The weight of the superstructure is 4,093 kilonewton. Is distributed over the quarter section of the ship length for 29 meter in the aft direction from the zero theoretical frame. So this consists as well the distribution of the superstructure to zero theoretical frame, and the rest of the ship mass, what we subtract from the light displacement of the mass of the superstructure, we can have 1,668 by 8 ton, the weight of 16,371 kilonewton, distributed along its length in accordance with the recommended scheme of Biles, the known scheme. So we consider the ship as the composition of 3 trapezoids, the 4 middle and aft, and this is recommended. Magnitudes of the factors of trapezoid, if we consider the light displacement we have with not the superstructure, and divided by the length by the waterline. So we consider length by the waterline. The middle part, 1/3 part of the length, a 4 part, and the after part, and the magnitudes of the extreme magnitudes of the linear distribution of the rest part of the displacement light by the length. The indicated diagram also shows the total distributed load acting on the ship, considering the minus sign of distributed force. So now we have the difference of the diagram. So if we have the diagram of the distribution of the ship weight, the ship weight is the ship itself and the cargo of the ship distribution by this one black pointed diagram. And we have this diagram of the strokes indicated the distribution of the submerged volume of ship, the same as the distribution of the Archimedes force along the ship line. We can find the difference. The difference is the solid line here. The difference is the resulted distribution of the load, of the external load acting on the ship as a result of an uneven distribution and unequal of the transverse forces of the buoyancy and transverse forces of the weight on the calm water. So we have the resulting distribution by the solid black line, considering the forces of the buoyancy and the forces of the weight. Forces of buoyancy we got by use of the theoretic frame. This is a theoretic frame, and considering the ordinates in the Excel table and using the formula of distribution of the submerged volume of the transverse sections by the length of ship, and considering the definition of the submerged volume, considering having the transverse section areas and finding as well the central location of the was the volume central location abscissa, and considering the ship of the parts of the lightweight and the cargo with ballast on one hand, and next the lightweight consider the parts of the ship hull and the ship superstructure together. Using the recommended formulas, we have the forces of weight of the ship, total magnitude of the weight equal due to the Archimedes law to the total magnitude of the weight of the submerged water. So, and but the distribution on the ship hull is not equal to these two forces and not even. So we have the difference, the two diagrams of the load and the floating force, the buoyancy force, and we have the difference, the solid. One diagram is distributed load. And considering distributed load, we can find the transverse forces diagram, and we can find the bending moment diagram on the calm water of the in the dangerous state of the navigation, where the ship have only cargo in the part of the cargo capacities, only one cargo of two cargo capacities. And if the ship have the ballast and the another one peak, due to keep against of the inappropriate trimming to exclude the slamming. Okay. And finding the values of the forces of the transverse forces and the bending moment, to find the values of the shear forces and bending moments in the cross section of each G's theoretical frame when determining the diagrams, one can use the numerical integration and the method of the trapezoid. A method trapezoid for the numerical integration. It is not so much different with the Euler rule to decide the differential equations for numerical decision of differential equations. It's about the same, looks like, but this factor is like, because we know for sure that the transverse force is an integral function relative to distributed load. And the bending moment is integral function due to the distribution of the transverse forces. So we have each next one magnitude of the transverse force as the previous magnitude, starting from 0. For example, we can start from 0. We can start here from 0 transverse force, moment from 0, because at peak we have 0. Transverse force, we assume that it's not very accurate, is not so much exact, because the ship is just, we are talking about the submerged volume that we appreciate. We assume that perhaps the ship excess in sizes over the length of the waterline, not so big, not impacting, just only by the definite appropriate error influence on the transverse force and bending moment. Although in the after we have a little bit discrepancy, this is characteristics of the extension of ship over the length of the waterline. But it is approximately not extended over the waterline, so we can start from 0. The initial magnitude of Q with index 0 with J, Qj is 0, 1, 2, 3, etc. number of the theoretic frame. So this is the formula, and this factor together as increment of the length space and the length of divided by 20 transverse frames. We have 20 spacings from 0 to 20, and this as well the longitudinal spacing. Then the factor is just a fraction in the numerator. This is arithmetic mean of the transverse forces at the end of spacing. Not transverse forces, but distributed load. The distributed load is the difference each. The Q is the difference of delta Q. It consists of the of two forces that resulting of two forces of the weight of ship and of the displacement of ship and the weight of ship. Yeah, as well, it could be the minus sign. The distributed load, distributed weight of the ship, not only load, but as well the light weight of the ship distributed by the ship. And the cargoes, not only load of the cargoes, but the cargoes of all variable loads. including the ballast, including the fuel for the ship consume, and this distribution of the Archimedes force along the ship. So, and the result will be the difference, and the difference we consider here, delta Q. The difference we consider as this delta Q. In the denominator, we have the arithmetic mean for each spacing, and this we can find by the numerical integration. Find what is the transverse force, and next we can having the transverse force find what is the bending moment. And this is the definite one section, and we got it. This is the diagram of the bending moment. This is the diagram of the transverse forces. Okay. Next, we have to analyze these diagrams. There is no cargo in the middle cargo tank in the ship without significant trim is in ballast, which, like the supply, the fuel, is shifted to the bow tanks. The bending moment has the greatest value of about 2,200 kilonewton by meter, corresponding to the 9th theoretical frame on the figure 7H3D. 7H3D. Theoretical frame, we have about 2,197,000, etc. So about 2,200,000 of kilonewton by meter in the 9th theoretic frame, like about in the middle of the ship. Sorry. Yeah, corresponding 9th theoretical frame. In the cross section of shear force is 0. Yeah, but in the middle we have the 0 shear force as its characteristic distribution. The shear force in the same frame, number H, we have almost 0 shearing force. Yeah. And in the cross section, at the first third of the ship length, both the bending moment is enough significant, 1,785 kilonewton per meter, and on the 6th theoretical frame section, in the shear force approximately 45,200 kilonewton are. Yeah, if you consider just only 6, a little bit to the bow. Yeah, the bending moment slightly less, but the magnitude not 220,000, but 100, not 2,000, 200 of kilonewton by meter, but about for the 6th, a little bit to the bow of the ship from the middle part. 1,785, etc. So about 1,800,000 of kilonewton by meter there for 6 theoretic frame. For J equal to 6 theoretic frame, this is a magnitude of the bending moment, and this is the same 6 theoretic frame. We have appropriately not so small. The shearing force is 45,189 kilonewton. So this could be the critical dangerous section for the consideration, considering the strength of the ship hull. Therefore, the check of overall strength of the ship below is proposed to consider bending and shearing on the section of the 6th theoretical frame, not in the middle, but in the 6th theoretical frame. This corresponds as well probably to the fore part of the cylindric insert of the hull. So the hull shape corresponds to the shape, the sharp shapes in the bow and the aft, and the cylindric shape equal almost for all the lengths of the cylindric insert in the middle part. And perhaps this middle part as it is for the middle transverse section, and perhaps this cylindric insert goes from 5th or from 6th theoretic frame until to the 15th theoretic frame. So, but we expect that this transverse section is almost within the cylindric insert of the hull of the ship. It is definite one section of 6th theoretic frame. We assume that the static bending moment is equal to 1,785,000 kilonewton by meter, and the shear force is 45,200 kilonewton. And the cross section located closer to the midship frame is on the 9th theoretic frame, in which the bending moment on the calm water is largest. It's about 2,200,000 kilonewton by meter, although the shear force in the section is practically 0. So this could be the suspect transverse sections on the 9th theoretic frame and on 6th theoretic frame for the assumed dangerous state of the navigation of the ship with the absence of the cargo in the middle part of the cargo capacities. Only in the stern part we have, and with the ballast in the bow peak of the ship hull. Questions and comments. 7.8.1. The greatest influence of the general loads acting on the sea displacement ship due to the uneven distribution on the length of the ship of its weights and the Archimedes forces in calm water and on waves, typical for ships of large size lengths as well as for the ships of the limited draft and the relatively small depths. For example, inland, mixed or coastal ships. Yeah, so if we consider the ship hull strength, there could be other concepts. We consider the concept of the general strengths. It could be as well the local strengths. For the small ships, could be the most important the concept of local strengths as the general bending moment and the general the shearing force is not so much important for the ship of the small lengths. Only the strengths of the floors of the any overlaps of the ship in the definite structural parts of ship side, ship bottom, etc. could be more important for the ship of the small size. But if we consider the ship of the big size or ship of the appropriately not so big draft and depth, so it could be more important the consideration of the general due to the expected elasticity of the ship. And we can expect the general bending of ships and general shearing, as we did for the ship for transportation of liquefied natural gas, like a bunkering tanker for transportation of gas. 7.8.2, the structural elements of a ship experiencing normal and shear stresses during bending and shearing under the influence of the weight and the Archimedes force unevenly distributed along the length of the ship. The deck plating stacks, bottom plating, second bottom plating, side plating, longitudinal braces, the keel stringers, carlins, longitudinal stiffeners, etc. I mean, longitudinal connections could be sheets of longitudinal bulkheads and double sides. Exactly for the ship of the big length and the small depths of the case, considering for the most critical loading of the general loading, general shearing forces and bending moment, the most important elements of ship withstanding the general load under the weight and under the buoyancy forces on behalf of water. Perhaps the most important is consideration of the longitudinal connections, longitudinal structural connections of the ship hull, which is longitudinal connections the most important which ensures the enough strength of the ship is the decks, is the bottoms, the plating of the decks, plating of the bottoms, plating of the sides, and all other longitudinal connections like keel, stringers, carlins, longitudinal stiffeners, etc. 783 common criteria and conditions when checking the overall longitudinal strength of a ship, the determination of safety factor of the material taking into account fatigue failure and the repeated cyclic bending of the ship experiencing alternating with bending moment, joint verification of the overall strength of the hull in bending and shear for the limit state, taking into account the impact possibility of the bottom on the surface of water during slamming as well as the bending moment in calm water. Yeah, this is what could be the criterion conditions for the ship under action of the general bending moment and general the shearing forces. As well, we have to, when considering the navigation state, to find the critical load. It's important that the navigation state have to be the realistic and relevant, we have to exclude the inappropriate duplicity of the factors impacting on the bending moment and the shearing force. What could be the duplicity? If we consider the ship and the action of the bending moment, so we can consider the bending moment with the use of the ballast to exclude the inappropriate trim if we have considered only the load in one of the load capacities, for example, which is the most dangerous could be. And to exclude the inappropriate trim, we have to assume that as well we have the ballast. The ballast another peak to exclude the inappropriate trim of the ship, which and exclude not only trim but exclude as well the possibility of the of ship hitting by the bottom on the water surface, which could be cause the impact and slamming, and this could be dangerous as well. But the result of action of slamming, but the action of the slamming could result into the loss of the strength due to the fatigue failure of the ship structures. This leads to adopt the safety factor to the permissible stresses. Safety factor with consideration of the to exclude the possibility of the fatigue failure due to the repeated impact of water impacts to the bottom of ship if we do not keep the trim. So on the other hand, we have whether use the ballast and another peak relative to the load in direction of the ship hull to keep the trim. This increases the bending moment and increases as well and shearing forces, and increases as well the equivalent stresses when we check the strength by the criterions of the strength. Or we have not to use the ballast if not. So this reduces the magnitude of the bending moment and shearing stresses. But in this case, if we don't use the ballast, we will have the opportunity to slam the impact of the water by the bottom due to the inappropriate trim of the ship. In this case, we have to increase the factor of the safety due to the exclude the fatigue failure of the ship. So we will not use simultaneously two factors, or the increase of the bending moment shearing forces due to use of the ballast in the peak excluding the inappropriate trim, and at the same time to use the safety margin of the normal stress to do the strength check, to exclude the opportunity of the fatigue failure. It's because we exclude the opportunity for fatigue failure by the exclusion of the slamming, by the increase of the bending moment and shearing forces, by the use of the ballast in the front peak. So we have to adopt only one assumption of two, considering the ship strengths. And this is definitely one case we adopt the assumption that due to the practical navigation, this is likely to adopt the ballast in the another one peak to balance the trim of the trim if the ship is partially loaded. This is more important, more characteristic for ship operation than to allow the trim and to allow slamming and to increase the safety margin, etc. This is not so much characteristic for the operation, for the calculation of the ship. So we have to adopt only one, with the exclusion of the duplicity in the criterion of the ship strength, 7H4. The obliquely symmetrical bending of connection structures considered when assessing the overall strength of multi-hull ships, the catamarans, trimarans, floating, semi-submersible platform, etc. Besides of the general shearing and bending of ship, of the big length and of the small depths, appropriately small to the length, and maybe the small draft. Besides of that, we have to consider checking the strength of the hull. We consider the general bending and the general shearing of the ship, no local but the general. First, besides, it could be another one shape of the bending of it could be the obliquely symmetrical bending. If, for example, for the multi-hull ship, we have the exceed of the, for example, the Archimedes floating forces applied to one peak of one hull and to other peak of another hull by the diagonal of the general arrangement of the multi-hull ship. In this case, we have obliquely symmetrical bending of the connecting bridge of the hulls. This could be as well the concept of the checking of the strength of the ship of definite classes. 785, finding the measured cross-sectional areas by numerical integration of the ordinates of the points of the intersection of the frames with the theoretical water lines using the method of trapezoid and the Excel, calculating area of diagram of the distribution of immersed volume along the length of the ship hull. Yes, this is a formula having the ordinates of the intersections of the transverse theoretical frames and the water lines. We can find in the intersection point, we can check the ordinates and we can set this ordinate into the table in the Microsoft Excel. And using this table, we can, for each of the theoretic frame, we can find the total of the ordinates and with the adjustment of the extreme two ordinates divided by 2 and multiplying that by the distance between each of two water lines, between each of two ordinates within the transverse section of the ship, we can find the submerged area of the ship transverse section. And we have, if we will do this for all the transverse section of the ship, we will have the distribution of the immersed cross-sectional areas by the ship. This is important to find the distribution of the floating force of the Archimedes and to find the point of the location of the submerged volume of the ship. And using the Excel, it's not a big deal. And we had the formula in the presentation 7H6 numerical integration by the method trapezoid, the curve for distribution of immersed volume along the length of the ship, how that is finding the immersed volume of the ship and the coordinates of the center of the immersed volume. This is a formal explaining how to find the submerged volume having the distribution by the length of the areas of the submerged transverse sections of the ship hull. We use the trapezoid method when we find the total of the squares of the submerged volumes and of all submerged volumes. In the considered issue, we had 21. From 0 to 20 is 21 submerged volumes. Formally, we have. And as well, we have to adopt adjustment for the extremal submerged for 0 transverse frame and for 20 transverse frame. Adjustment we had to the final result of the total in accordance with the trapezoid method. And besides, we have to multiply that to the theoretical space and the distance between each two theoretic frames, transverse sections. 7.8.7, the approximate determination of the distribution on the ship length of the sum of main components of its weight, the empty ship cargo and ballast in the absence of the detailed data of the design of ship. At the initial stages of the ship design, we have to do the calculations and the check of the strength preliminary, but sometimes we do not have enough information about the actual distribution of the load. So we can consider the ship load consisting of part, not only load, not only cargo, sorry, but the load of the cargo and of the ship empty itself. So we consider the variable loads as the fuel, as the ballast. We consider the cargoes. We consider the empty ship weight, lightweight so-called, and we consider the lightweight consisting of the parts. Could be the part of the ship case itself and the weight of the superstructure. And we have to adopt this always to the segment of the ship length. So then we can find the distribution of the cargo along the length. We have to find this distribution corresponding the same numbers of the theoretic spacing as we have for the forces of the Archimedes distribution by the theoretic shape of the ship. Then we can find the difference. The difference is the distributed load, non-even and non-equal uh, for the buoyancy. And then for the cargo and for the load, distributed gave us different differences. The distributed load action on the ship hull, and next we can use a numerical integration and find the transverse forces, and the second numerical integration find the bending moments action on the ship. 788, the distribution of ballast when the ship is partially lowered in order to balance the trim and eliminate slamming the impacts of the bottom and the bow on the water surfaces and waves. When calculating the load in the option of the exclude slamming, the combining of the prerequisites which associate with the loads from the ballast and supplies fuel are received to the bow ship, considering when finding the overall bending moment and the shear force. As a prerequisite to find the bending moment and shear force, we have to find it for the check of the ship strength. Thus, we have to find the bending moment shear force for the dangerous state of the navigation of the ship. Dangerous state could be if we have the ship partially loaded, and the ship partially loaded, for example, if we have two separate cargo capacities, we can consider loading only one of two cargo capacities. Which one? It could be if you have the equal ones, not the middle cargo capacity, but to the any peak, to fore peak or to the stern of the ship. We have considered the field and the another one empty in the middle of the ship. And besides, we have to adopt the definite ballast and the stocks as a fuel and fresh water for the ship consume. And another peak to keep the keep balance of the trim in the appropriate level, to exclude the slamming, because this consequently we can in the check of the strength not consider so much as the fatigue possibility of the fatigue failure, which can be the result of the slamming, fatigue failure of the ship. So if we do increase the bending moment and shearing forces by the adoption of the ballast to exclude the slamming, this increased, on the other hand, the bending moment shearing forces on the calm water. This increases the forces we next used for the checking of the general strength of the ship hull. So in this case, we do not need to consider the fatigue failure, because it will be the double checking of the overestimation of the external loads. If we will assume that we don't have the slamming if we adopt the use of the ballast. 789, approximate determination of the light weight of the ship distributed on the lines using the recommended scheme of the Biles for finding the bending moment and the shear force when checking the overall longitudinal strength of the ship. The diagram of the distribution of the ship light weight according to the recommendations of the Biles could be as the simulation of the ship distribution of load of the weight of itself weight. The light weight of the ship is like three parts of the trapezoid shape. The middle part of the shape of the rectangular, and the bow and the aft part is the shapes of the trapezoid, so the shapes of the diagram. And recommended as well as magnitudes of the linear distribution of the load by the Biles. 7.8.10 diagram of the total distributed load acting on the ship as the sum of diagrams of distributed Archimedes force and the weight force, taking into account the minus sign for distributed force of the ship weight. This is perhaps understandable, no big deals. It's only if we have to know that is how to find distributed force, as there is a difference between the Archimedes force directed upward and the load force directed downward. The result will be the distributed load action on the ship, cause the shearing force and cause the bending moment, general bending moment of ship hull. 7.8.11, using the method of trapezoid for numerical integration of distributed load when determining the general diagram of the shear forces and the integrating diagram of shear force, general diagram of the bending moment. We use the differential interdependence of the indexes of the distributed load, of the transverse forces, shearing forces, and of the bending moments, because each next one is integral of the previous. So thus having the distribution of the of the external load, we can find the shearing forces as the integral of the distribution of the load on ship as the difference of the Archimedes forces and the load forces with cargo ship and separately cargo with the ship together combined in the load. And after that, we can find the integral function, which will be the bending moments integral by the reference variable of the ship length. 7 and 12 location of the middle part of ship hull of critical cross-section considered when checking the overall strengths differing a little structural elements. For example, the sections of cylindrical insert of the ship hull or close to the insert on which the greatest general bending moment of maximal shear force acts together with sufficiently high bending moment. Yes, so after finding the diagrams of the general bending moment and the shearing forces acting on the ship hull, and the next issue is to indicate what is the critical sections, critical transverse sections of ship. This critical could be all the sections with a maximal bending moment or maximal shearing forces, or with a significant shearing forces or bending moment if they are together in definite one or few sections, transverse sections. So this could be the critical transverse section subject to the next check of this of the ship general strengths. 7H13 systematic methodological approach that eliminates the duplication of overall strengths while taking the account the following conditions: the cyclic action of loads and the corresponding safety factor of the material, the ratio of the yield stress and equivalent stress at critical points selected in critical cross-section. Additional load arising when receiving ballast to exclude unacceptable trim and slamming the static position of the ship on top of wave, the length of which is commensurate with the length of the ship, taken into account by use of the dynamic coefficient of the total load found in the calm water. So when we consider the factors impacting the state of the ship shearing and the general bending, so we have to assume that could be it's not very probabilistic to consider together of other factors simultaneously sometimes, because some of them excludes the other factors. As we told about the factor of the slamming caused the possibility of the fatigue failure of the ship by the cyclic loads. On the other hand, can be excluded itself by the use of the ballast in the bow, in the peak bow sections of the ship hull, for example. And in this case, it's not so much logical to consider together the increase of the bending moment caused by the reception of the ballast and to reduce the permissible strength caused by the possibility of the fatigue failure, because the reception of the ballast reduces the possibility of the fatigue failure itself. So this all is the assumptions for the calculation. We have to obey the duplicity, or with no balance with the slamming, but with the considering of the extra safety margin to exclude the possibility of the fatigue failure, or we exclude the fatigue failure with not a increase of the safety margin, but with the increase of the bending moment, considering the reception of ballast in the before or after peaks of the ship hull. Thank you.